Nozzles and diffusers make good intuitive sense for incompressible fluids, but what about the case where we actually have a flow that is compressible and specifically compressed as a result of its supersonic motion? There you may have trouble developing your intuition, so we'll walk through how this works. I conducted a numerical simulation where a flow is proceeding this way in the directions indicated by the arrows, but there are those gray structures that are intended to mimic rigid structures. So the red part is the fluid has to flow around those rigid gray triangles, and this flow is governed by this equation given in your lecture notes that relates the area, the velocity, that's v, and the Mach number m. Remember, the Mach number is just the ratio of the velocity to the speed of sound in the medium. Okay, so let's think about this for a moment. First, let's deal with the area, because that dA term can be kind of confusing. All the sign of dA tells you is whether the flow is geometrically constricting or expanding. So on the left side, since the flow is approaching a smaller and smaller area as it goes forward before it crosses the triangles, there dA is less than 0. That tells you that the flow is being geometrically restricted by these rigid objects that are preventing the flow from just going straight through. Likewise, on the right side, after it passes the points of the triangles, dA is greater than 0. That means the flow has the possibility of expanding. The area expands so that it can move out. Okay, so that's what's going on with dA. Now the Mach number for a supersonic flow has to be greater than 1. So in that case, 1 minus m squared must itself be a negative number. Okay, so what does that mean? On the left side of this flow, dA is less than 0, and 1 minus m squared is less than 0. That tells us that actually dV must also be less than 0 in order to cancel out that negative sign in front of it. You have to track the negative signs pretty carefully here. There were 4 of them in that statement. So we would predict that dV will be less than 0 on the left-hand side. Well, what does that mean? As the flow proceeds, as it's approaching the points of those triangles, we expect the velocity to drop. Now that's different than a nozzle for an incompressible fluid where the velocity should increase as the area decreases. In this case, we're going to see the opposite happens, and that's because we're moving supersonically with a compressible ideal gas. On the right-hand side, of course, you can probably follow the trend. Since dA switched its sign, dV also switches its sign. So actually, on the other side, where the flow is geometrically expanding, we expect the velocity to increase in this case, again because of supersonic motion. Now, you probably would never believe me because those results are so counterintuitive unless I did the simulation. So I did it. Let's watch the animation. So the red fluid being visualized actually corresponds to the velocity. If you see the red get brighter and whiter, that means it's a higher velocity. If it gets darker and blacker, that means that it's a lower velocity. Let's see what happens when I start it. Passes through, and sure enough, on the right side of the triangles, you see this really high velocity region. So the velocity is increased in that bright sort of orangish yellow region. It is decreased on the left. It's become really dim and black. That's a lower velocity than we started with. So that's what happens when you have supersonic flows passing through weird geometries. They do things that might run counter to your intuition. If you're interested, this structure is known as a de Laval nozzle. You don't necessarily need to know that for this class, but it's true. That's its name.